Okay, for problems 1 through 8 in the data listed in table 16.2, design a plane surface bearing using the boundary lubricated approach of section 16.5. Use an length to diameter ratio for the bearing in the range of 1/2 to 1.5. Compute the PV factor and specify material from table 16.1. So this is, I'm going to work problem 16.7. It's on page 579 for the sake of the video. The radial load that's given is 800 pound force. The shaft diameter is 3 inches. The shaft speed is 350 revolutions per minute. Okay? All right, now the other constraint is that the length to diameter ratio should be between 1.5 and 1/2. So essentially we're going to have a bearing that has some length L and some diameter D. Okay, it's that ratio that they've told us to control. So we're supposed to use the approach in 16.5 and compute the PV factor and specify material. So let's go do that. All right. There is a design procedure for this. It's on page 651. So I'm simply going to follow it. That's the easiest way to go through this. Given information, radial load on the bearing, speed of rotation, nominal minimum shaft diameter. 561. I'm sorry. What did I say? I'm sorry. 561. I don't know what I said. Objectives of the design to specify the nominal diameter and length of the bearing and a material that will have a safe value PV. Specify trial diameter D for the journal and the bearing. Okay, no big deal. They've already told us that, right? It's 3 inches. So diameter, 3 inches. Specify a ratio of bearing length to diameter. Typical range is from 1/2 to 2. We're constrained to be from 1/2 to 1.5. For non-lubricated, dry rubbing, or oil-impregnated porous bearings, length to diameter ratio of 1 is recommended. For carbon graphite bearings, length to diameter 1.5 is recommended. We don't know what this is. I'm going to assume that it's oil-impregnated bronze because that's fairly cheap. If you ever take apart a power drill or power tool, you'll probably find oil-impregnated bronze bearings on the motor itself, and maybe even on the gearing. Anyway, so I'll just use a length to diameter ratio of 1. You don't have to. This is a design decision. If I come back and find out I've got a problem, here's 1 degree of freedom I can use to vary the design and hopefully overcome the problem. Compute the length, equal diameter times length to diameter ratio. Obviously the length in this case is just going to be 3 inches because the length and diameter are equal. Specify a convenient value for L. Well, this is already a convenient value. A lot of times when you specify this ratio and you have some odd diameter, you end up with an odd length. So you just round up or down to a standard size. Compute the bearing pressure in pounds per square inch or pascals as pressure equals load over L over D. Now I used R for the load. He's using F in the design procedure. Same difference. So R is 800 pounds. Please pull out your calculators. I didn't prepare this one beforehand, so just grab your calculators. Basically what I need you to do is divide 800 by 9. 88.88. It's almost 100. 88.88 PSI is the design pressure. Now why do we care about that? Well, we care about it because that's the load that's going to be applied to the bearing. So let's see. Compute the linear speed of the journal. Now, your author has several different equations here that are convenient, and so it's worth putting a tab in this design procedure. But this procedure, of course, is only good for boundary lubrication. This is not for full film lubrication. That's a little more in-depth. But all of these equations are based around the idea that the velocity would be omega cross r. I don't know if you guys remember that from dynamics, but if you have the radial distance from the center of rotation out to the point where you're interested in the velocity, you cross that, actually you have to make a cross that with the angular speed in radians per second, you'll get the velocity, the tangential velocity. Since this has some conversion factors in it, if you have an angular speed in revolutions per minute, your author is giving you some convenient equations. And our particular equation, we're in US customary units, so it will be velocity is pi dn over 12. So if you're wondering where the 12 and the pi came from, essentially they're conversion factors. They're conversion factors so that we can use diameter in inches, that's what the 12 is for, and in RPM rather than in radians. Okay, so let's just plug it in. Pi by 12, 3.0 inches, and the speed, 350 RPM. And the velocity should come out in feet per minute. So if you guys would calculate that, I would appreciate it.
274.75.
So there's the velocity in feet per minute. The next thing to do is to compute PV, the PV product. Notice we've got the pressure here, we've got the velocity here, and so if we multiply the pressure times velocity, let's start over up here, that's essentially the amount of power that the bearing has to take. Okay, so 88.88 psi multiplied by 274.75 feet per minute. And you could round this off. You could take this to 89 or 90 times 275 if you wanted to. It really doesn't matter. How much did you say it was?
24,432.
24,432.
432.
Thank you. And that's PSI, feet per minute. Those are the units that we have. So all we need to do is find a material that can take that. And if you look, I'm sorry. So if you look over at the table, you might be tempted to pick DP11 dry. Do you see that that can take 28,600? But actually what we're supposed to do is design for twice this. Okay, so it's about 25,000. So I'm looking for something with about 50,000. And so porous bronze, oil impregnated, BU, dry lubricant bearing, DU, whatever those two other materials are, I'm not familiar with them. They would in theory work for what we've got. So that's really step 8. It says multiply 2 PV to obtain a design value for PV. Specify a material with the rated value of PV equal to or greater than the design value. It's not really a surprise that 2 PV is about 50,000 PSI feet per minute. And so I'm going to just choose oil bronze. Okay, so oil impregnated bronze is what I would select. And so basically the rating is exactly 50,000 PSI. You don't have to. I mean, you could go up from there if you wanted to. You could easily go up to aluminum bronze if you wanted to. It would work fine. It's just probably a more expensive material. Okay, specify material, we did that. Complete the design of the bearing system considering diametral clearance, lubricant selection, lubricant supply, surface finish specifications, thermal control, and mounting considerations. Often the supplier of the bearing material provides recommendations for many of these design decisions. Basically, what your author is saying there is you're not done because there has to be some clearance between the journal and the bearing. But at this point, the material dictates those things. And so you go to the manufacturer of the material and ask them what you do. Okay, so you will have some clearance. Notice that 3-inch diameter, that is a nominal diameter. The actual diameter of the bearing in the journal will be different. Okay. Nominal diametric clearance has many factors affect the final specification of clearance, such as the need for precision thermal expansion of all parts of the bearing system. Other variations, shaft deflection expected, means of providing lubricant and manufacturing capability. One long used rule of thumb is to provide 1,000th inch of clearance per inch of journal diameter. Figure 16.4 shows recommended minimum values for clearance based on journal diameter and rotational speed under steady loads. These values apply to the smallest clearance under any combination of tolerances on the dimensions of the bearing system to avoid problems of bearing heating and eventual seizure. The operating clearance will then be higher than these values because of manufacturing tolerances. Performance over the entire range of clearances should be evaluated preferably by testing. Basically what he's saying is this is a complicated problem. But this chart gives us a minimum amount of clearance. And so you have to tolerance the journal and the bearing such that you always have at least that minimum clearance. Because if the journal were to heat up and the bearing didn't, the journal is going to expand and it might seize. We need to avoid that. So really the last step in this procedure for our class is to look at figure 16.4 and decide what the clearance should be based on this. Now this is a minimum clearance. So if the journal diameter is 3 inches and the speed is 350 RPM, then what do you guys think the clearance should be?
What page are you on right now?
Page 561,
Okay.
figure 16.4.
Is that the?
Suite 0025?
Yeah, 0025 is reasonable. Everybody understand where you got that from? Okay, there's a 3-inch bearing, this nominal diameter. If you go up to a speed of 350 RPM where they intersect, it's over a little bit because that 3-inch mark is to the right of the 75 millimeter a little bit. About 2.5. Okay, now what I would do, I would just bump that up to 0.03 of an inch and be done. Now this is the, I'm trying to remember if this is a, yeah, these are diametral clearances. It shows at the bottom.
You said
Is it?
4 thousandths.
Hmm?
What you also say?
We're saying about 2.5 thousandths. Okay.
So you got 3 inch.
Yeah, so 3-inch, you come up to a rotational speed and
Oh,
revolutions per minute,
okay.
RPM,
Yeah.
350. You're about between those two. For the sake of the video, I'm going to point it out because it seems like we're all struggling to understand it. It's pretty straightforward. All you do is you select the journal diameter down here, the nominal, so it's about a 3-inch diameter. You go up to the speed, in this case we're on the inner y-axis, 350 RPM, and wherever that is. Now that ends up about halfway between the 0.02 and 0.03 of an inch diametral clearance lines. So we're saying about 2.5. Now notice that means that you'd have half of that clearance on one side of the bearing and half on the other nominally. Okay? Any questions on this problem? It's a fairly straightforward thing. It's not difficult to design boundary lubricated bearings up to this point. After this, there's a lot more to it. And notice your author even suggests that testing would be suggested. Okay?